Hello, Year 12. I just want to spend a bit of time today just looking again at the increasing and decreasing function things and perhaps clarifying a couple of things that I maybe wasn't awfully clear on. Before I do that, next week, obviously you're not in on Monday, you are in on Tuesday. So what I'm going to do is I'm going to do a video for Group 12E who would have a maths lesson on Monday. And then I hope that 12B, I can teach an equivalent lesson to you face to face on the Tuesday. So everyone will have the same amount of maths, it's just 12E will have it by video and 12B will have it face to face. Of course, there is the chance that 12B, you'll be getting tested during my lesson. I don't know when all that testing is going to be happening for you, in which case we've got the video as well. So I'm hoping that by Wednesday, when I see both groups, we'll all still be up to date, and we won't have one group who's a lesson ahead. So I hope 12E are not too grumpy about having to do a lesson on Monday. I'll try and make it light as A-level math gets anyway. Right, so we were talking about increasing and decreasing functions, and we've got these two approaches, haven't we? The turning point approach and the inequality approach. Now, I think if you're dealing with a quadratic, and you use the turning points approach, it's okay to say, right, I found that this is a minimum. This one would have a minimum, obviously, because it's this shape. And I know what shape it is. Therefore, I know it's decreasing before the minimum and increasing after the minimum. I think it's really important to make reference to the shape, though, because otherwise, who's to say where it's increasing, where it's decreasing? If you use the inequality approach, it's not a problem, is it? You just either say, right, when is it greater than 0? That's going to be where it's increasing. When is it less than 0? That'll be where it's decreasing. If you use the turning points approach with a cubic, you'll find your two turning points, and we know what shape a cubic is. I still think, in the spirit of belt and braces, I would go on and just confirm that the first turning point was a maximum and the second turning point was a minimum. I think, I can't say for sure whether that's necessary, but I'd still be tempted to do that. Again, if you use the inequality approach, it's not a problem. You'll get a quadratic, and it's just solving that quadratic inequality. And in the work that was submitted, we had a mixture of people using both approaches. When it comes to other functions, so these are ones that are a bit weird and wacky and we don't know the shape of. Well, don't forget we've got the graphical calculator, which we can use to check. We can't use that as evidence in our answer, though, and it sometimes isn't particularly helpful. But I would suggest that with ones that are weird and wacky, the inequality approach is nearly always the best. And I don't think I was perhaps very clear about that. You can use turning points, but I still think that inequality is easier. So let's use this as an example. And the reason I'm using this as an example is this was actually a question from the 2019 AS paper. Okay, so and I've got the mark scheme here as well. So let's use this example, and let's start by differentiating it and using the turning points approach to locate any turning points on this curve. So that's when dy by dx equals 0. So go on, pause and have a go at that for me. Okay, so I'm hoping you rewrote it like this before you tried to differentiate it, writing it in index form. 2 times 3 is 6, reduce the power by 1. Minus 1 times 24 is minus 24, reduce the power by 1. The 2 disappears. And this is a key thing that a couple of people got wrong. That means this. It doesn't mean 1 over 24x squared. It means 24. The 24 isn't involved in the negative power. It means that. Now, actually, although in the mark scheme I've got here, it says that you have to have it written in that form there. It says lower down in the notes that it would have accepted this. Okay, but I still think this is easier, because what you're then going to do is go on and find the turning points by asking where does it equal 0. Hopefully you've already had a stab at this. Multiply by x squared, divide by 6, add 4, so my turning point is, and there's one of them, is the cube root of 4. The cube root of 4 is not plus or minus when you cube root, so there's only one turning point. But of course, I still don't know at this point whether that's a maximum or a minimum. I've probably got an idea because I've probably already sketched it on my calculator. So we need to differentiate again to work out what sort of turning point that is. So if you have a go at that for me. Okay, so I've differentiated again. Remember, this means that. Substitute my x value in. That gave me a positive answer, so I know I'm dealing with a minimum. Now, so if I've got a minimum, does that mean that everywhere to the left is automatically always going to be decreasing and everywhere to the right will automatically always be increasing? Well, pretty much. And in fact, if I sketch this particular function, I find that there's my turning point. And yes, although it's not continuous, it's one of these functions that sort of disappears to infinity and then reappears. It is decreasing everywhere to the left of that turning point, and it is increasing everywhere to the right. And I think at this level that's probably okay, but it is possible to have a function that, say, has a minimum and then maybe disappears off to infinity and then maybe reappears at infinity and comes down and and has a weird and wacky shape like that. So in that case it wouldn't be decreasing before and increasing after because it starts decreasing there again. So I think that's why I would probably choose with weird and wacky functions to use the inequality approach. And so I'm just going to focus again. I'm certain that you'd get full marks at A level if you then said, okay, it's a minimum, so we're asked to find where it is increasing, so it would be when x is greater than the cube root of 4. But I think I'm going to use the inequality approach because I think that's absolutely guaranteed to confirm it. So I'm going to, my inequality approach, I'm going to start like this. That's dy by dx. And if I'm looking for where it's increasing, I'm looking for where that's greater than 0. So not where it's equal to 0, but where it's greater than 0. And obviously the process is pretty much identical to the turning point process. So I'm going to multiply by x squared. I'm going to divide by 6. And there's my answer straight away. Okay, straight away. I know that, I've asked when is the gradient greater than 0. So this is asking when is it increasing, and bang, got the answer straight away. So that's much easier than this. Now, my fondness for the turning point approach, I think maybe confused a few people, and certainly I prefer it with quadratics and cubics. But when you get to these weird and wacky ones, yeah, the inequality way is much better, and it guarantees that you get the right answer rather than just assuming that a minimum will always have decreasing to the left, increasing to the right. So I would recommend that you use that. Now, did you notice, if you looked in the textbook at any of the answers, that they would have written that answer like that? So they would have done it by asking when is it greater than or equal to 0. Now I don't agree with that, because when the gradient equals 0, the function isn't increasing or decreasing. That's the turning point. And in a second textbook that I looked in, they agree with me. So I thought, oh dear, what does the exam board think? And you will be relieved to see that the exam board doesn't care. So if I show you the mark scheme for this question, the mark scheme says they will accept either what I would write or what the textbook would write. Note though that they use my method. So they are basically saying when is it greater than 0? So they agree with me, they think this is the best, but they are also saying they will accept that. I don't know why the textbook chooses to use that approach, but I'm sticking to my idea that a function is increasing when dy by dx is greater than 0, decreasing when it's less than 0, and has a turning point when it equals 0. So let's just look at the submission question. I think this one a weird and wacky one. This one is so much easier to use inequalities than looking for turning points. I'm going to sketch it first, which is always my suggestion. And when I sketched it, it looked very odd. That's with the V window set to standard. But of course, if I zoom out, you can start to see it. So actually, I have got two turning points. And if you look for turning points, you've got turning points at -5, that's a maximum, and +5, that's a minimum. So you can solve this question using turning points. But I would still say that the fact that you don't have to go on and investigate the nature to prove that's a maximum, that's a minimum, means the inequalities approach is much quicker. So f dash of x, I'm going to differentiate this, so x becomes 1 minus 25 x to the -2, which is 1. So I am going to ask, I want to find, I forget what the question actually said. The question say increasing or decreasing? It's decreasing. So we're asked to find when it's decreasing. So it's decreasing when the gradient is less than 0. So I'm going to multiply by x squared. Don't need to worry about flipping the sign because x squared is always positive. Remember, with inequalities, if you do something that involves multiplying or dividing by a negative number, you've got to flip the sign. This is a quadratic, so I can either add 25, but that causes a bit of confusion with square rooting because you've got two possible answers. So instead, I factorised. And remember, although the original function is a weird and wacky one, what I'm trying to answer this question, when is this decreasing, I'm asked, when is this quadratic less than 0? So I know the quadratic has roots at 5 and -5, and I know what a quadratic looks like. So when is the quadratic less than 0? Well, it's less than 0 between 5 and -5. So that's when that function is decreasing. Now, there's an extra little issue here, and you see that issue when you look at the graph, because this function isn't defined when x is 0. X can't be 0, and if you look at the original function, you see why. When x is 0, you'd get math error, wouldn't you? Because you can't divide by 0. So actually, we can't have this range of values. It's not decreasing in this range of values because 0 falls in between those range of values and it can't be 0. So actually the strict answer to this question would be that we've got that and we've got that. Now I didn't correct people that put that in the submission question because I think that's, correct and would get you full marks, but actually to be strict, that's the correct answer. That is when the function is decreasing. Now you would have got the same answers by using turning points, and you would have got full marks for turning points. But I think the inequality approach, when you've got weird and wacky functions, is going to be easier. How did they get in that exam question we did to start with? How did they get round the x can't be 0 problem? Because they've got the same issue here. Well, look what they said. They said we're only ever going to make x positive, so they solved it by that thing there. Okay, moving on. Okay, so this question we're asked, is this function an increasing or a decreasing function? So an increasing function is one that is always increasing, and a decreasing function is one that is always decreasing, rather than being a mixture of both. So go on, just pause and have a look for turning points, differentiate it and have a look for turning points. Okay, no turning points. So, however you did it, there's a number of ways you could have done it. You should have ended up with x squared is -1. X squared can't be -1, so we've got no turning points. So we can't differentiate again and find the nature of the turning points. So we're a little bit stuck here. I mean, I sort of know that these graphs, a negative cubic, always look like that. So maybe it's suggesting that it's one like this, so it's always decreasing. But I think it's a bit unsafe to say that with no more evidence. Of course, I can use my calculator, and the calculator confirms what I thought was true. But again, I can't use that as evidence. So again, we're being forced down the inequality route, and we are going to have to try and use inequalities to demonstrate whether this is an increasing or a decreasing function. So have a think about how you could do that. Pause and have a go. I'm going to go through a solution in just a moment. Now, I'm not saying this is the only way you could have done it, but I've got my dy by dx, obviously that's the same as going the other way, and I'm asking, is this always positive or always negative? And so I've done a bit of proof by deduction. I know that x squared is always positive or greater than 0, greater than or equal to 0. So minus 3 times that, because I've had to multiply the inequality by a minus number, I've had to flip the sign. Still 0 though. And then if I take away another 3 from that side, well, if it was equal to 0, it's now definitely going to be less than 0. So I know that this is now less than 0, so the function is always decreasing. I suppose you could say less than or equal to minus 3 there as well, which again would demonstrate that it's always negative. But I think, you know, that's a good way of doing it. What you're basically showing is that this is always negative. And you could have done it with description. You know, minus 3 times x squared will be negative, so taking away 3 from that would be negative as well. I think this is, you know, there's one of a number of ways of doing it. So I think turning points again, bit of a blind alley. Inequality approach provided the best option there. Okay, so finally with this, here's a function that you may remember what it looks like. If not, you can sketch it. And so this is clearly one of those functions that's increasing before 0 and decreasing after 0, and we're being told that x can't be 0, which solves that little problem that we have with dividing by 0. But how do we actually show this? Well, it's a weird and wacky one, so I'm not going to look for turning points. I'm going to use the inequality approach. So I'm going to rewrite it as, go on, can you differentiate it for me? And then think about what the inequality approach would involve. Pause and have a go. Now, what we'd normally do at this point is multiply by x cubed, wouldn't we? But the trouble is that 0 is your friend normally, but it's no help this time, because that would just give you minus 2 is greater than 0, which isn't true, and this would give you minus 2 is less than 0, which is true, but doesn't tell us anything about x. So in this case, we would just need to use some common sense. And it's helped by the fact that I've been able to sketch it. So I already know the answer. I know it's increasing when x is less than 0 and decreasing when x is greater than 0. So this is an increasing function when dy by dx is greater than 0. And for this to be greater than 0, this would have to be negative, because then you'd have a negative divided by a negative, which is positive. So this is true when x is less than 0. So when x is less than 0, when this is negative, x cubed will be negative as well, and therefore you'd have a negative divided by a negative, which is positive. This will be true when x is positive, because you'd have a negative divided by a positive, which is negative, which is less than 0. So that's true when x is positive. So we've got here a sort of common sense explanation for when it's increasing and when it's decreasing, and yeah, that's a valid approach. So I wasn't able to use algebra here, but I suppose it's a bit like proof by exhaustion. So I've sort of said, okay, let's sort numbers into positive and negative and deal with it like that. So I would, you know, don't forget that sort of common sense approach to problems like this. That's a perfectly valid way of doing it. So of course I want to state my my final answer. So it's increasing when x is less than 0, decreasing when x is greater than 0. X can't actually be equal to 0 itself. Right, enough increasing and decreasing. And I think the other thing I need to say is, actually, I've looked at some really quite complicated examples, but the vast majority of questions I found were cubics. You had to show when cubics were increasing and decreasing, and that's easy. you can do that, and you can use turning points or you can use inequalities. So I hope I haven't frightened you too much. And so my submission question reflects that fact. So can you just tell me for that cubic where it is a decreasing function? And then, so that's the submission question. But some of you might be thinking, I really need some more practice. So there's a mixture of differentiation questions from the mixed exercise at the end of the chapter. So 12E, you'll get a video from me on Monday, and 12B, I certainly hope to see you in class on Tuesday, and certainly we'll all be back in class together on Wednesday. Take care.